Good evening, everyone. I welcome everyone to the KAAPI with Curiosity talk today. And I would like to call upon our director, Dr. B.R. Guruprasad, to welcome the gathering.
Good afternoon to all of you, and welcome to yet another lecture under the program KAAPI with Curiosity. It's a joint program with International Center for Theoretical Sciences. Both JNP and ICTS are partners in this, and I thank ICTS for arranging this lecture. Very, very interesting one today. And Madam Yvonne Wong has come all the way from Sydney to deliver this talk. The topic is, as the title itself says, when big meets small, the connection between particle physics and cosmology. And I don't want to preempt anything. Let her say and let her detail about this subject in her talk. Welcome to you, madam, on behalf of JNP and ICTS, and welcome to all of you. Thank you very much. Sharanya.
Thank you, sir. I request Professor Joseph Tamil from ICTS to introduce the speaker.
Thank you. It's my pleasure to welcome and introduce our speaker today, Professor Yvonne Wong. She works at the University of New South Wales in Australia, Sydney, Australia, and her interests are at the interface of particle physics and cosmology. Now, you might wonder whether there is such an interface at all between the big and the small, and that's where her slide brings out the message that she's going to convey. When the universe was much smaller and it was also very much hotter, physics was very much determined by the interactions between elementary particles. There are many relics of this period today, including the relative abundance of the elements in the universe and also the cosmic microwave background. Professor Wong's interests are in cosmological constraints on elementary particle physics. She is particularly interested in the most elusive of fundamental particles, the neutrino, and the even more elusive cosmic neutrino background. Apart from chasing these cosmic phantoms, Professor Wong is also an accomplished pianist.
You know that?
She's here to share her excitement and knowledge with you today. So here's Professor Wong for you.
Well, thank you for the introduction. I hope it's not too loud, okay? Okay, so I'm here to tell you about the connection between particle physics and cosmology. So first of all, well, that's the word cosmology. What's cosmology? Well, Well, cosmology is basically the study of what the universe is made of, its structure, its origin, and where it's heading in the future. Now, of course, these are age-old questions that have been attempted, whose answers have been attempted by many different cultures. But of course, these days when we talk about cosmology, what we mean is physical cosmology, which is a science. And in other words, when you do science, you have observations, data, okay, experiments or observations, and then you try to come up with a theory that is grounded in some mathematical framework to try to describe what you've seen. And then you tested your theory against further data, you refine your theory, and the cycle continues, okay, until you find a theory that describes what we see in experiments or observations. So, the first assumption that goes into modern cosmology is called the cosmological principle. And essentially, what it says, the cosmological principle, is that when viewed on a large enough scale, the universe is homogeneous and isotropic in space. Now, these two words, homogeneous and isotropic, sound like the same thing, but actually they're not, because homogeneous means same everywhere, whereas isotropic means same in every direction. Okay, so this universe here is isotropic, but it's not homogeneous. This universe is homogeneous, but it is not isotropic, so the planes are moving in the same direction. And this last universe here is homogeneous and isotropic. So I had better rephrase the cosmological principle too. When viewed on a large enough scale, the universe looks the same everywhere and in all directions. An immediately corollary of that is that where we live here in the universe, this patch of space that we live in the universe, is actually not a special place at all, because it's the same everywhere. Now, is there any truth in this? I would say so. This is a map made by the 2-mass redshift survey. And essentially what they've done here is to map out the local galaxies around us out to a redshift of 0.03. Now, if you're not familiar with the measure of redshift, this is a distance measure, essentially. And roughly that redshift of 0.03 corresponds to a distance of 370 million light years. In other words, the median distance in this collection of galaxies here is, if you want to get to them, it will take light rays 370 million years to get to. Okay, so each dot here is a galaxy. This black strip here is black because when we're making observations within the Milky Way, and the Milky Way has a lot of stars in it, so we can't look past the Milky Way. So we have to kind of look in the direction that is perpendicular to the galactic plane, and so we can't map the galactic plane. That's why it's black. But if you just ignore this black strip here in the middle and just look at the upper hemisphere and the lower hemisphere and squint your eyes a little bit, it looks pretty uniform. Okay, so we say that yes, it looks like the universe is quite homogeneous and isotropic on scales that are larger than about 300 million light years. Okay, so having established that homogeneity and isotropy is a pretty good description of our universe, what we can do next is to find a theory. Oh, by the way, just to give you an idea of what these distance measures, the Earth to Sun, the distance is 8.3 light minutes. So light takes 8 minutes to go from the Sun to the Earth. Okay? Now, having established that homogeneity and isotropy is a pretty good idea to describe a universe, the next thing we can do is to apply a theory of gravity. Okay? And the most famous theory of gravity that we have, best theory of gravity that we have at the moment, is that of the general theory of relativity, or so-called general relativity. That's Einstein's theory of gravitation, which he came up with in 1915. And essentially the idea is that instead of describing gravity as Newton did, as a force, you think about gravity as an effect on the space-time geometry. Okay? So such that if there was no gravity at all, then this space-time manifold that we live in would be flat, and everything moves in a straight line. Okay? But since we know gravity exists, and there's a lot of stuff around that is causing things to gravitate, then what this stuff does, essentially, is to curve the space-time. And so you can look at this picture over here, and get this picture over here, where you have some stuff there in the middle, in this form of this little ball, and it is bending the space-time around. And imagine if you want to think about something analogous, think about a piece of rubber and put something in there, something heavy in the rubber, and the rubber will bend. Okay, this is exactly what's happening here. Your space-time will bend as a result of there being stuff. And the amount of stuff that is there, the more stuff that you put in, the more curvature that you would expect in the space-time. And that in mathematics is described by what is called Einstein's equation, which is essentially this thing here that's shown on the mug, and that relates the distribution of the stuff in this parameter t mu nu to the curvature of space-time, which is described on the left-hand side of this equation. Now, what's more, if you have curved space-time, then things traveling in this space-time will no longer move in straight lines, but rather they'll move on a path that is bent. But that's exactly what we want, right? We want to describe how things get bent as a result of the influence of gravity. And this description of gravity in terms of the geometry of your space-time gives you exactly this bending behavior. And so these bend paths that you see here are called geodesics, and they are the shortest distances that things will travel on in a curved space-time. Okay? So a nice analogy of what's happening is that you can think about the Earth, which is like a sphere, and the surface of the Earth where we live, and it's curved. Okay? And you think about trying to travel from one place to another across long distances. These paths here that are usually taken by flights are more or less a geodesics. Now, there are other factors, of course, affecting flight paths, like the streams and weather and maybe political situation, but more or less flight paths are geodesics. Okay, so you wouldn't go. This is Seattle over here. This is Munich over there. If you want to go from Munich to Seattle to Munich, you wouldn't just go across like that, because that is not a geodesic. But this path here over Greenland is a geodesic. So we have homogeneous and isotropic description of the universe. That's what we learned. And we know that stuff bends space-time. So what happens now if I have a universe that is filled with homogeneous and isotropic stuff? Well, that's exactly what these four gentlemen thought about back in the 20s and the 30s. Alexander Friedman, Georges Lemaitre, and Robertson and Walker. They thought about what happened if you have homogeneous and isotropic stuff, and how the gravitation of this homogeneous and isotropic stuff would mean for the universe. And what they found was that space expands in such a universe. And today we call this expanding universe the Friedman-Lemaitre-Robertson-Walker universe, or FLRW for short. Okay. And the expansion rate is given by an equation called the Friedman equation, named after Alexander Friedman. And essentially what this equation tells us is that the expansion rate, square, as a technical detail, is proportional to the energy and density of stuff that you have in your space. So in other words, how much energy do you pack into a volume? That's density. And it depends on the geometry of space. Now, you may have heard about expansion of space under a different name, namely Hubble's law. And Hubble's law states that two galaxies, if you look at them, they move away from one another at a speed that is proportional to the distance between them. And so these are actually the equivalent statements, because if I look at this piece of bread here, if you imagine that two galaxies are like represented by raisins, then indeed it's the case that, oops, what happened? The raisins will move apart from each other as this bread expands uniformly in a way that is proportional to the distance between them. Okay? So these two are equivalent. Now, of course, when Hubble came up with this law, he was not baking bread. He was actually observing galaxies. And this is his data. And he was basically measuring the recession, how the distances of galaxies away from us, from the Milky Way, and how quickly they are receding from us. And this is what he got. And the slope here, this is distance, and this is the speed. And this is the data he has, and the slope here is Hubble's expansion rate. Okay, it's described by this law. V is equal to hd, and h here, the slope, is called the Hubble parameter. Okay. Well, actually, Hubble was a bit lucky because he actually measured the expansion. He got the expansion rate really wrong. His data was up here. Modern measurements since the 60s have actually put the expansion rate at a much lower value, maybe a factor of 10 difference. So Hubble was wrong by a factor of 10 due to a calibration error in his instruments. But nonetheless, he got the idea right. And these days, we have much better measurements where the error bars around this expansion rate is at the percent level. Okay, so we have established that the universe expands. So what can we conclude on this basis about the past of the universe? Well, since space is expanding with time, what it means is that if I wind the clock back, then the universe must have been a lot smaller in the past. Okay? But if I still have the same amount of stuff in the universe and you pack them all in a tinier space, that means everything was denser. Now, if I compress things, they also get hot. Okay? So the stuff was hotter. In other words, they had more energy. So what we can conclude from on the basis that the universe expands is that if I go back to the very distant past in the universe, the further back in time we look, then the denser and the hotter things must have been. And from there, we get this picture that is generally accepted as the history of the universe today, that illustrates how we got, this is today over here, but back in time, the universe was a smaller place, and at the very, very distant past, we would have started with extreme density and extreme temperature, and at that point, that was called a Big Bang. Okay, so this is the history of the universe. Now, there are many stages in this history of the universe that is interesting, but let me just first of all point out this place here, which corresponds to a time when the universe size was 1,000 of its present size. Okay? And that is because once you get to, once you wind the clock back to this time in the universe, the temperature was also much higher. It was also 1,000 times hotter than it is today. Okay, so the temperature at this time here would have been about 3,000 Kelvin. And this is interesting because if you remember, you have 3,000 Kelvin, that is almost as hot as the surface of the sun. Okay, surface of the sun is more like 5,000, but 3,000, that's pretty close. Okay? And at these kind of temperatures, an interesting thing can happen. You can break up your atoms. Okay? Atoms are normally consisting of, like a nucleus in the middle, and then you have electrons around it. The simplest one would be the hydrogen. You will just have a proton as the nucleus, and then you have one electron orbiting it. But when things get so hot, to the point of being 3,000 degrees Kelvin, then what happens is that the extreme amount of energy that is present there would actually allow the electron to be kicked out of its orbit from the atom. So instead of having a nice neutral bound state hydrogen, what you have instead is actually an ionized plasma of free electrons that are floating around and free protons. And this is very interesting because this actually directly limits how far we can look back in time. Okay, and the reason is as follows. If you go to temperatures that are about 3,000 degrees Kelvin, and you have a lot of, and as I said, you have a lot of free protons and a lot of free electrons around, then what happens with photons, which is essentially a quantum of light, is that these photons, these light particles, instead of traveling in straight lines, will start bouncing off the free electrons that are there in the plasma. They encounter an electron, they bounce, they encounter another electron, they bounce again, and every time they bounce, they change direction. So instead of just going through straight like so, they are doing what is called a random walk in this soup of free electrons and free protons. So that if I am an observer trying to look into the sky at what's happening in the very distant past, I don't see anything because the photons are not getting to me. They're doing a random walk. They don't escape this soup of stuff to come to my telescope for me to see what's happening. Okay? Conversely, if I lower the temperature, so allow the universe to expand a little bit, and the temperature drops down to below 3,000, then what happens is that the plasma is no longer energetic enough, and the free electrons and the protons would prefer to combine back together into neutral atoms. And in that case, you no longer have these charged particles all over the place for the photon particles to bounce off, and now the photons, the light particles, can travel in straight lines. And once they travel in straight lines, they can travel to infinity without encountering anything else to bounce off, and then I can see it. Okay? And this is analogous actually to something that we are very familiar with in everyday experience. If you look into the sky and you see a cloud, you can't see beyond the cloud. Okay? And that is because when you have a cloud there, it's basically a lot of water droplets, and that actually has the same effect as having a lot of free electrons. You're basically making the photons do a random walk within your cloud. And so I can't see beyond the cloud. I can only see up to the lowest part of the cloud. Okay? And that essentially is what we call the last scattering surface, and that is because that's the point at which the photons will scatter the last time before traveling in a straight line to the observer. Okay, so we have a similar thing also when we're looking back in time in the universe. There's also a last scattering surface corresponding to the time when the photons stop doing their random walk and then want to travel in a straight line to infinity to the observer today. Now, these photons that have come to us now is the oldest light that we can see in the universe, and it's called the cosmic microwave background. Okay? When they were first formed, when they first start moving towards us, they were very, very hot because they came from a soup that was 3,000 Kelvin in temperature. But the thing is that between them being starting to move towards us and us observing now today, the universe is also expanding. And that leads to an effect called shifting, which essentially means that the photons become cooler and cooler and cooler. And so that today, when we look at these photons again, we're not seeing these photons with a temperature of 3,000 Kelvin. We see them with a very, very tiny temperature of 3 Kelvin only. Okay, so that's just 3 degrees above absolute zero. This was first predicted by, this effect was first predicted by Alpha and Herman already back in 1948. And this background was discovered in 1965 by Penzias and Wilson. They were actually engineers. They were not really looking for the cosmic microwave background. What they were doing was just trying to detect radio waves. And when they saw this background, they did not know what they were looking at. And they were trying to figure out what it could have been. And they thought about all sorts of possible sources that may have given them the signal. And at one point, they were even considering things called white dielectric material, in other words, pigeon droppings, to see if that might have been the source of their signal. But no, in the end, they talked to some cosmologists and realized that actually some people already predicted this background, and they got a Nobel Prize for their discovery in '78. And today, we have much better measurements of the CMB. It's in fact the most perfect black body that we have ever measured in nature. This measurement here was from 1994, from the FIRES instrument on the KAAPI satellite. And what they measured was this really nice Planck spectrum for these photons that come from this last scattering surface. And the error bars over here have actually been blown up 400 times because it's such a fantastic measurement. It's such a fantastic measurement that if they plotted the real error bars, you won't see them. Okay? And this excellent measurement has, the temperature, by the way, has also been measured to a very high accuracy. And this measurement has led to a Nobel Prize being awarded to John Mather and George Moot. And today, we have seen several more generations of the CMB measurements. So this was the original from Penzias and Wilson. That was the KAAPI measurement in the 1990s. And in the noughties, we also had the measurement of WMAP, so the Wilkinson Microwave Anisotropy Probe. And most recently, in 2013, we had the measurements from Planck. Okay, that's an ESA mission, European Space Agency mission. What's even more interesting is that, rather than just measuring it, is that if you look very closely, there are these tiny little fluctuations. They are not noise. Actually, these fluctuations are 1 part in 100,000, and they were actually already predicted back in the 70s by Peebles. Okay, and these fluctuations had to they had to do with the basically the initial state of the universe, and as I said, they were already predicted by Peebles back in the 70s, and he was awarded a Nobel Prize in 2019. So this video here is a video of the ESA Planck mission and what they were doing. So as a satellite mission, which was launched in 2009 to the Lagrange points, and what they were doing is that they were measuring photons coming from extragalactic space and microwave frequencies, and they were scanning the full sky in this fashion. And so this is going to take a while to scan the full sky. Now, the thing is that with microwave measurements, it's actually quite non-trivial, and the reason is that there's a lot of things in the galaxy that are also emitting at microwave frequencies. And so in the end, what it means is that after you do the scan, the map that you make will be kind of dirty and noisy. Okay, so first of all, you see not the microwave background, but you see the galaxy, okay, over here, in microwave frequencies. And there are all sorts of foregrounds that have nothing to do with the cosmic microwave background that we have to remove. They're individual sources. These have to be removed. And then you have to remove all the radio emissions from the Milky Way itself, which you do here. And also dust emissions, which also have to be removed. And finally, once you've cleaned the foregrounds completely, what's left is the microwave background that is primordial in nature, coming from the last scattering surface, and that's what we really want to see. Now, these fluctuations are they look like just noise, but they're actually quite amazing because they reveal not only the composition of the universe at the time of the last scattering, but because the photons from the last scattering surface have to travel to us, and they have to travel long distances before they get to the observer, it turns out that these photons that we observe today will also carry information about the composition of the universe today, and the spatial geometry as well. And since these photons must have come from somewhere, and these fluctuations must have come from somewhere, they will also carry information about things that had survived down to CMB times. Okay, so there's a lot of information about studying these fluctuations, the statistics of the fluctuations in particular. And when you've probably all seen the picture over here, this cosmic pie, which tells us about the composition of the universe today. Most of this information actually came from studying the statistics of the fluctuations of the cosmic microwave background. Okay, so today we know that we have 72% of the composition of the universe in the form of a mysterious dark energy. We have about 22% in the form of dark matter. And ordinary things, atoms, people, makes up only about 4 or 5% of the energy density of the composition of the universe today. There's also a trace bit of neutrinos, which I'll talk a little bit more about later. Okay? So, that's the cosmic microwave background, but we need not stop there, because we can keep dialing the clock back and ask what happens. And indeed, if the higher the temperature you go, the more interesting things can happen. You can venture into the nuclear physics regime where nuclei break up, and if you go even further, you venture into the particle physics regime. So first of all, if we turn the clock back to, if we shrink the universe to the size that is about 100 million its present size, we get to temperatures that are about 50 million Kelvin. And that kind of temperature is comparable to what you can expect in a fusion reactor or in the core of the sun. Okay? So, in these times, the light elements of the universe were formed. Light elements up to carbon, roughly. Okay? And the theory, the processes, and the theory that are behind this is called Big Bang nucleosynthesis. And that was already discussed back in 1948 by Alpha, Beta, and Gamow. And essentially, the idea of this theory is that you start with a bunch of neutrons and protons, and through a series of nuclear reactions, okay, you can form deuterium, tritium, helium, various isotopes of helium, lithium, beryllium, all the way up to carbon. That's really what's happening in a fusion reactor. Okay, and in the universe, early universe, you have a natural fusion reactor that makes all these light elements for us. Going back even further in time to the time when the universe was 1 part in 10 to the 12, its present size, we reach a temperature of 4 trillion Kelvin. And at these extreme temperatures and energies, even the protons and the neutrons will break up into its constituents. And the current standard model of particle physics tells us that neutrons and protons are actually composites of quarks. And if you get up to these extremely high temperatures, then you can even break up the neutrons and protons into what is called quark-gluon plasma. So you have free quarks that are flying around, as well as the gluons, that is the glue that is binding these quarks together into bound states. Now, just to let you know that the quark-gluon plasma is actually something that is also studied in colliders. There's a special kind of colliders called heavy ion colliders. There are a couple of them at the moment. There's RHIC, which is called a relativistic heavy ion collider at the Brookhaven National Laboratory in New York. And the LHC at CERN is also capable of doing this kind of heavy ion collisions. And what they do essentially is to collide beams of gold ion together or lead ion together, and then let them smash. And then what comes out of it at the other end is this hot soup of quark and gluons. Okay, so these quark-gluon plasma is being recreated in these laboratories in order to help us understand what happened in the early universe. And going to even higher energies, we reach a point where the typical energy of the particles in the universe even exceeds the highest energies that can be made in a collider like the LHC. And and it goes on. Now, what lies beyond that at these at energies beyond LHC energies? Well, frankly, we don't know, because we can only, we only know what's happening at a collider if we that has been tested at a collider. But more fundamental theories may pop up. Maybe we have supersymmetry or extra dimensions, quantum gravity. But at the moment, no one can really say. But the expectation that everyone has in the cosmology and particle physics community is that the physics in this epoch, these extremely high energies, will probably allow us to solve several open questions in cosmology. Okay? So what? Then I move on to my next point. What can particle physics do for cosmology? Well, as said, there are some open questions in cosmology, and that's basically represented by this pie over here that I just showed, which shows the composition of the universe today. Now, a lot of people will say that we don't understand 95% of this pie, but I think we don't really truly understand any of it. The first thing that we don't really understand, well, the most famous thing that we don't really understand is probably dark matter, which makes up about 25% of the present-day composition of the universe. So, what is dark matter? Well, dark matter was already studied back in, the word dark matter was actually first coined by Fritz Zwicky back in 1933. He called it dunkle Materie, which is German for dark matter. And essentially what he was doing was that he was looking at the coma cluster, and he noticed that what he can actually observe doesn't correspond to the mass that he thinks the cluster should have. And so he figured that something must be dark. Okay, that was already back in 1933. No one cared about what he said, really, until the 70s, when 60s and 70s, when Vera Rubin really studied the rotation curves of various clusters and galaxy clusters and determined that, yes, Fritz Zwicky was not just joking. He actually was onto something. Okay, and today we know from cosmological and astrophysical observations that this dark matter is a slow-moving kind of thing. Okay, it's not moving at the speed of light. And it is not normal matter, in the sense that we're not looking at we're not talking about asteroids that are not emitting light, or brown dwarfs, or anything that's not emitting light. And it said, well, it doesn't emit light. But the thing is that even though we know what it is not, we don't know what dark matter actually is. And that's where particle physics can help us, okay? And in fact, many particle theories of dark matter that have been proposed. And the idea is that if you extend the standard model of particle physics, then most of these extensions will contain a particle that will serve the purpose of the dark matter. It will be probably massive, or maybe it's light, but in any case, you can make it slow-moving. They would not interact much because they are a particle that is beyond the standard model. So, and since we haven't seen them yet, they probably don't interact much. Now, this picture here shows you all the basically particle theories that have been proposed. It's unfortunately not very easy to read, but I'm not asking you to read it anyway because there are just too many of these theories. But roughly speaking, if you look at the landscape of dark matter particles that have been proposed, they range from very tiny masses to extremely heavy masses. So if you go, these are all the different candidates that have been proposed, and this scale here basically gives you the particle mass. Okay, if you're not familiar with these units, the electron mass is 500 keV or so, the proton mass 1 GeV. So you have dark matter candidates that are extremely massive, that are tens or hundreds of times heavier than a proton, as well as dark matter candidates that are much millions and trillions of times lighter than the electron. Okay? They are usually classified as wave-like dark matter and particle-like dark matter. And the classic particle-like dark matter is called the WIMP. And the WIMP is a weakly interacting massive particle. Okay? And the expectation of this WIMP dark matter is that it should have a mass that is about 10 to 100 times the mass of the proton. And it should have weak each kind of interaction so that it can be produced by scattering in the early universe at an extremely early time. Okay, so the idea is that you think about some ordinary matter particles from electrons, protons, and other standard model particles. They can scatter off each other, and during the scattering, they can produce two dark matter particles. Okay, so that's how we expect this WIMP dark matter to have been formed in the early universe. And since we are surrounded by dark matter today, as we have dark matter in the universe is surrounded by the dark matter today, so if we are in the Milky Way, we are sitting in a dark matter halo, then we can actually try to detect this dark matter by putting detectors on Earth. Okay, and so that if we just put a detector there, and one of them might come into your detector and deposit some energy in your detector, and then you have detected dark matter. Just to give you an idea of how many dark matter particles we have, if you go order mass of beer, that's about 3 WIMP particles in this mass of beer. Okay, so that's basically how these direct dark matter detection experiments work, and there's a lot of them around the world, all over the place at the moment. Most of them are underground, well, actually all of them are underground, and you need to do these experiments underground because these detectors are just sitting there waiting for dark matter particles to fly in and deposit energy, right? But there are many other things around that are not dark matter that can also deposit energies. So they have to put the experiments underground in order to shield all of these events, these background events that you don't want. Okay, so they're all underground. There's actually also one in Australia, but this is a slightly old picture. There's also a dark matter experiment in Australia. So that's a WIMP dark matter particle, which is the classic dark matter. But as said, there are also many other dark matter candidates around, and my personal favorite is actually axion, which is kind of wave-like dark matter. And these axion dark matter particles are very, very, very light in mass. And in fact, if you compare these axion particle to the mass of the electron, they're about 1 million to 1 billion times lighter than the electron. And but what's cool about these extremely light particles is that, well, first of all, there's a lot of them. So if I go back to this mass of beer again and ask how many axion particles do I expect, we're talking about 10,000 trillion axion particles in this mass of beer. But what's even cooler about these axion particles is that instead of moving around like particles, they're very slow moving and they like to move as one, like a wave. Okay, so we call this wave-like dark matter because of this coherent behavior of these particles. Okay, it's like a condensate. Okay, and these particles would also have been produced in the early universe at an extremely early time. And in particular, they are formed through a series of phase transitions, where phase transitions happen when you have more symmetry and then you break down to lower symmetry and etc. And here's a little picture here that is actually done by my former PhD student of a simulation of axion dark matter production through a series of phase transitions. And what you have here are basically these what we call axion strings, and they are evolving and connecting and breaking up. And then when they break up, they emit some more axions. In the end, what you see here are these little clumps of axions, which are basically seeds for clumps of asteroid mass dark matter that we should expect to see in the solar neighborhood. So this is something that we can, that is also being, that people are also devising experiments to detect. Okay, so that's dark matter, but of course that's not the only thing. That's an open question. We also have dark energy, which is something that is quite mysterious because it's not like anything that we know. It's not probably not a particle. But the general expectation is that this dark energy is probably going to be explained by the temporary creation and annihilation of virtual particles and antiparticles that are allowed by the uncertainty principle. And if these virtual particles and antiparticles gravitate, then the gravitation of this kind of stuff would lead to a phenomenon that is like the dark energy. But at the moment, this idea doesn't completely work. And to make it completely work, we'll probably need a theory of quantum gravity for that. Now, you can debate whether this is particle physics territory again, but still it has something probably related to some high energy fundamental physics in the end. Also, this slice here, I'm labeling atom at 4%. Now, you may think that we understand atoms because that's just ordinary matter, but actually that's not quite a complete picture, and that is because if you look at the standard theory of Big Bang, you produce a lot of matter and antimatter, at in the earliest instance, right after the Big Bang. But as it turns out, for us to end up with just a tiny little bit of matter and not much antimatter, there's a lot of fine-tuning that must have happened in the early universe. So you must have produced just a little bit more matter than antimatter in the early universe in order to end up in this situation in the present day. Now, why that is so, we don't really know, but there are many theories around that might explain it, and some of them may even have to do with neutrino physics. Okay, so that's that. Now, so I talked about what particle physics can do for cosmology, but I can also turn it around and turn the question around and ask, well, can cosmology do something for particle physics too? And as it turns out, the answer is yes, and it's here in the neutrinos. So, as I'm showing you here, this pie over here contains this tiny little slice over here that is less than 2% neutrinos. So the neutrinos make up a very, very small fraction of the universe's present-day composition. Now, I write smaller than 2%. I don't have an exact number attached to it. And we don't know that exact number because we don't know what the neutrino mass is. Okay? Oh, by the way, the neutrinos are these very light particles in the standard model of particle physics. Okay? They are the lightest and most weakly interacting of all the known particles that we know. Now, as said, you know, we have this smaller than 2% here in this pie because we don't really know what the neutrino mass is. If we knew what the neutrino mass is, then we can be more certain about exactly what is the contribution of these neutrinos. But as it turns out, now, of course, we can do experiments in the laboratory to try to determine its neutrino mass. But as it turns out, the best place to find an answer to what the neutrino mass should be is actually in cosmology itself. And that is because we have these neutrinos that are in the universe, and they are participating in all the events that in the evolution of the universe. And just by virtue of being there and being a kind of energy density that's just sitting there, these neutrinos actually have an impact on the way how galaxies and galaxy cluster formation should evolve. Okay? And in the end, it turns out that exactly what mass these neutrinos should have actually has quite a strong impact on the final distribution of galaxies and galaxy clusters in space. So this here is, well, a couple of simulations that show a cosmology with zero neutrino mass on the left-hand side. And on the right-hand side, we have a cosmology that has some amount of neutrino mass, okay, 2.3 electron volt, so that's about 200,000 times lighter than the electron. And this simulation box here is about 800 million light years across, and you can think about each dot here as a galaxy. And what you see is that even though these two boxes started off exactly the same, because they evolve into different configurations, because on the right you have zero neutrino mass, on the left you have a final neutrino mass. And the key difference between these two simulations is that the cosmology that has a zero neutrino mass has a lot of really fine structures. You know, all these really fine dots over here. This one here on the right-hand side, on the other hand, has the gross structure. So you have like a big filament over here of galaxies that's also present over here. There's a big empty region called void, which is also present here. But you don't see the fine little dots, okay? Simply because the neutrinos are massive, okay? And this is very powerful because we can go and measure the distribution of galaxies. I already showed you one of these maps before. This is another one from the Sloan Digital Sky Survey. This is a bit old, but the picture is very nice, so I'm showing it. And you can see that each dot here is a galaxy, and then you see these filament structures, you see voids, and etc. So what you can do is to compare the theoretical prediction, like the ones that I showed you in the previous slide, with an actual observation of the galaxy distribution, and from there to deduce what the neutrino mass must have been. Okay? And And I'm actually finishing a bit early, but I think that's all I have to say today. So I hope I've convinced you that particle physics and cosmology are somehow interlinked. And I leave you here with just the history of the universe. So thanks for your attention.
Yeah, we can have a few questions. Please put up your hand if you want. Just a minute. Yeah, start with you, please.
My question is that how do neutrinos determine the distribution of galaxies and the galaxies clusters?
Yep.
That is number one. And number two, you show the components of a neutrino, those lightly interacting particles which you had shown. Have they been observed in the Large Hadron Collider, LHC?
Okay, so the first question is that neutrinos, when you make them in the early universe, they move very, very fast. They're relativistic particles, so they have a lot of energy. And as the universe expands, they lose some of this energy, but because when they were made, they were so relativistic and fast that even after the expansion, they don't lose enough of this energy. So when you form structures, what happens when you form structures is that you have what is called gravitational collapse. Okay, so you have things that are getting dense and they collapse on themselves. But if your particles have a lot of energy, they don't like to collapse. They like to fly out. So if some of the stuff in the universe is in the form of neutrinos, then it changes the way things clump. And that's why it is that you have, when you go back to look at this picture of the neutrino distribution, you don't have these small structures, because on these small scales, the neutrinos are moving too fast to clump. That's the reason. So that's the first question. Neutrinos have, of course, been observed. They've been observed for a long time. In fact, you have there are a lot of natural sources. There are neutrinos coming from the sun. There are neutrinos coming from the upper atmosphere, from cosmic rays bombarding on the upper atmosphere. We have reactor neutrinos coming from nuclear reactors. And LHC, well, I mean, they can make neutrinos in a secondary way, but that's not their purpose. But sure, you can also use an accelerator to make a neutrino beam. And, but that's something that people do. At Fermilab, for example, in the US, they have an accelerator, make a neutrino beam to do experiments on the neutrinos. Yeah, yeah. That's what I
Yes. Why do free neutrons decay into protons?
It's allowed because it's heavier. Basically, the rule of thumb is that anything that is heavy, provided the interaction exists, will decay. So the neutron is heavier than the proton, and the weak interaction is there. The neutron participates in the weak interaction, the proton as well, and so the neutron is allowed to decay into a proton. Yeah.
So neutrino observatories like Ice Cube, so like do they merely detect neutrinos or can we study the mass of them as well?
Well, the ice cube neutrinos are extremely, extremely energetic. We're talking about more than TeV. We're talking about EeV. I don't even know what E stands for in this case, or how many zeros follows that. These neutrinos are so energetic that the mass is a tiny fraction of their energy. So you can't really study the mass of these neutrinos. What you can try to do is to look at mass differences. So what people do is to look at flavor composition of these neutrinos in ice cube and determine neutrino oscillations. So you can look for mass differences between two mass eigenstates of the neutrinos, but to determine the absolute value is not something that ice cube is capable of.
Hello.
Yeah.
Regarding that, the wave-like picture of dark matter. So, does it actually tell something about the quantum nature of dark matter, or is it simply a classical wave description?
The wave-like dark matter?
Yes.
That is just a wave description, a classical description of waves. It's nothing quantum. It's just that they move coherently as one. So you write down a wave equation to describe them. It's classical.
Okay, thank you.
Yeah.
Firstly, it was a great talk. And my question is, currently there are 3 generations of these fundamental particles, right? So there are 3 neutrinos. Is there any way theoretically that there are more neutrinos, lighter probably? Which we
Theoretically, yes. Theoretically, yes. I mean, these neutrinos usually go under the umbrella term of sterile neutrinos. Sterile in the sense that they are not part of the SU2L gauge group. Okay, in other words, they don't participate in the weak interactions. Okay, so theoretically, yes, you could have neutrinos that are fairly light, but they would not be like the standard kind of neutrinos. Yeah, but it's possible, sure. People write down theories of that nature.
Greetings, ma'am. Ma'am, if the percentage of dark matter is way more than baryonic matter, why is it only present in the center of the galaxies? And why can't we measure it anywhere else, like in the solar system?
Oh, that is simply because of gravitational clustering. So in structure formation, the idea is that you start with some perturbations in the density field, and gravity will tend to make those areas that are dense, originally dense, even denser. And those regions that are empty, even emptier. So if you let this whole system evolve for long enough time, you'll always end up with a lot of empty regions everywhere and clumps. It's just gravity at work.
So like if we go back in time, like a few million years ago, you can estimate
More than a
it
few
to be
million.
anywhere, everywhere.
Yeah, so it's a CMB times, for example, which is 13.4 billion years ago. The distribution of dark matter is fairly uniform. It's just that when gravity is allowed to kick in, then that would tend to amplify those dense regions into even denser regions, and empty regions into even emptier regions.
And now if we extrapolate it, where can we consider it to? Like, would it be at the center of the universe, or like, would it be at one point of the universe? Or
Say again, yeah.
like, if we extrapolate it and go into the future, all the dark matter, will it be like clumped into the center of the universe, or?
No, they won't, because like they would just be well, there are many galaxies, right? So the current understanding in structure formation is that you have each galaxy is enclosed in its own halo, and so you just have, if you go further forward in time, you just have these units. Okay, maybe they'll merge, but you wouldn't just have one single point, because they are, once you have a merger, there will also be merger happening here, and yeah.
Oh, I also have
That
2
one.
more
Sorry.
questions.
Yeah.
Sorry. So please correct me if I'm wrong, but is it true like neutrinos oscillate between the 3 types, the tau neutrino? So
Right.
all these things, how, and the mass varies. So like how does the mass oscillate between those? Do we have a theory regarding that? And another question is, does dark energy has any sort of impact with the temperature of the universe?
Okay, so first, neutrinos. So the reason you have neutrino oscillations is because, okay, you remember quantum mechanics? Well, maybe a little bit. Yeah. So there's a thing called mass eigenstate. Okay, so that's basically neutrino. You can write down the neutrino wave function in terms of the mass eigenstates. So you decompose it in terms of the masses. Okay, but when the neutrinos interact, the basis of the interaction is different. Okay, so what we say is that you have to use a mixing angle to kind of transform from the mass basis to the interaction basis, and that is what is causing oscillations. Okay, this mismatch in the mass eigenstates and the flavor eigenstates, because it's the mass eigenstates that determine how the neutrinos propagate, but you're interacting in the interaction basis. And so when you have this kind of thing happening, what it means is that over time the masses are kind of traveling a little bit differently, and then you'll have a phase difference between the different mass eigenstates. Maybe that has to be taken off. We can discuss this offline. Yeah. What was the second question again? Dark energy. And the dark energy, yes. So dark energy, it depends on exactly what the dark energy is. it will change the expansion rate of the universe. So the expansion rate of the universe depends on the kind of stuff you have in there. So if you have only non-relativistic dark matter, the universe would expand in one way. If you have very energetic radiation, the universe would expand a little bit differently. Dark energy is a different kind of stuff again. And in fact, dark energy causes the acceleration to be, the expansion to be accelerating. Yeah, so that does change the temperature of the universe through the way the way the universe expands. Yeah, that's a question over there, or maybe two even. Right.
Why did dark matter form? Like, how did it form?
They would have formed in the very, very early universe, and the expectation is that they formed. I can't really quantify it in time. Maybe it's in this picture, probably. Would it be 1 part in 10 billion of a second, roughly, after the Big Bang? Yeah. So when the universe was extremely hot and extremely energetic, yeah.
Is there any relationship between expansion of universe and energy of neutrino?
Energy of the neutrinos?
Yeah.
Yes, not so much today, but at early times, the energy of the neutrinos would drive the expansion of the universe. Not today, but if we go back to...
Why not today, or what is the relationship?
Okay, so if you go into these very early times, like 1 second after the Big Bang, the neutrinos play a very important role in driving the expansion of the universe. That is because...
That means neutrinos are pushing objects in that time?
Well, in those days you had no objects, because the formation of structures only begin at a very late time. The neutrinos are important around here.
What type of particles were there at that time?
At this time, neutrinos, electrons...
When neutrinos are driving the expansion... They are
not the only things driving the expansion, but they are one of the many things.
What type of particle were they?
Other elementary particles, like, so we have a... hang on, where is it? Where is it? Here. So you have essentially around that time you have all of these standard model particles. They would all have been responsible for driving the expansion at these very early times. Yeah.
Okay. So now, no influence on expansion.
These days, no, because at the moment, as I have shown in this composition, the neutrinos are only making up less than 2% of the stuff in the universe. So they are not really doing much anymore. Just like the photons are not doing much. What is driving the expansion is mainly the dark energy.
Okay, thank you.
Yeah.
That's a good lecture, thank you.
Yeah.
Hi, you said your particular favorite for dark matter candidate is QCD axion. Is there a particular reason that you prefer that over other candidates?
I don't know, I just like it. But I think I like it because the physics is interesting. I think plane scattering is kind of boring. The fact that I have to study a phase transition and see how things form, and then you have defects. I like it because of that. I don't think it's any particularly. No, it is quite well motivated. So axions are not just something that was invented to explain dark matter. There was actually another reason for for inventing the axion. That's called a strong CP problem, and it is a fundamental problem in QCD. And axion was invented to solve that. And then it turned out that it could also make a very good dark matter candidate. So for me, first of all, it's two birds with one stone, so that's nice. And also the phenomenology is very rich. So I like it for that reason. Yeah.
Hi.
Oh, sorry.
It's a very abstract question that I have, okay? We started off with an assumption that universe is homogeneous. Now we are part of universe in some way, right? We are. So assuming that I'm part of universe, then I would have all the dark energy, the dark matter and neutrinos and even atom to some extent inside our own body. To some extent, I myself might be a universe altogether. But going to that, more subtle, understanding on a more subtle level, which is non-physical in its very nature. Can we ever measure that, because it's, at the end of the day, we are trying to measure something which is, I feel, non-measurable in a way. So if you could shed some light on it.
So first of all, I wouldn't say you have any dark energy or anyone has any dark energy in them. That is because we compare with the scales that we're talking about, we are very, very minute, we're tiny. And whether anyone is made out of dark energy depends on whether the dark energy likes to clump into small places. And if our current understanding of the dark energy, look at most dependable or probable model is that it's a cosmological constant, and this kind of thing doesn't clump. Yeah, if the dark energy is a cosmological constant, it doesn't clump into little things, little clumps. But atoms will clump. So we are atoms. We're not dark energy because the dark energy doesn't clump. Okay. So that's in response to your comment. When you say we want to measure dark energy, what do you mean? Like measuring it in a lab? Or that is hard. It's unclear how anyone would do that. Yeah. Yes. Yeah.
There might be things that might be also there present in our body, but probably this is because I started off with the first assumption that we are homogeneous, right? We're part of the universe. I mean,
yeah, but the homogeneity in isotropy is only applicable on extremely large scales, because we know that on small scales things are definitely not homogeneous and isotropic. We exist, therefore that already breaks that assumption. But that's why when we say homogeneous and isotropic, we always say on large scales. And that large scale is 300 million light years.
But if we go more finite,
yeah, if you go finer and finer, then all of these equations that describe in expansion of the universe, they don't even apply.
Yeah,
they don't even apply. So we don't talk about. It doesn't make sense to talk about individual people expanding.
Yeah, but if you look more finite, right? I mean, there is energy, subtle energies in us. So there is something more non-physical that we are only not able to measure. So we think it doesn't exist. Right? But what if there is? But it's only because we are unable to measure at this point of time. We think that there might not be a part of us because
that's possible. But yeah, okay, fair enough. Yeah. But the thing is that these, as I said, the most probable explanation of the cosmological constant. I mean, I would prefer it anyway if it works out. It's something to do with quantum mechanics, quantum fluctuations, and these are things that are present. Yeah, according to our current understanding of quantum mechanics, quantum field theory, these virtual particles are always popping out and disappearing all the time. So they are there. It's just that on large enough scales, they also, well, hopefully gravitate in a way that would drive the accelerated expansion. But again, as said, we don't have a really full theory to describe that. It's just general expectation that this is how it will work.
Just one last question.
Where? Sorry. Okay, yeah.
Okay, so this is regarding dark matter.
Yeah.
So recently there have been many alternate theories that disprove dark matter, and one of it is MOND. It's called modified Newtonian dynamics.
Yeah.
So I wanted to know your opinion. Maybe there is like a fundamental theoretical origin for MOND, and it does not involve maybe dark matter.
So, okay, MOND. So a lot of people studying MOND are looking at rotation curves. So they're looking at like a galaxy or a galaxy cluster, and then they say, how can I tweak Newton's law away from 1 on r square, inverse r square law to account for the rotation curve. Now, you can certainly play that game, but the thing is that I think from my point of view, the evidence for dark matter is not just coming from rotation curves. It's also coming from, well, you have bullet cluster, you have lensing, and most of all, you have the CMB. And describing the effect of, describing the CMB using MOND instead of dark matter is very, very hard. And I think that's where MOND fails. It's not like you can't do it, people have tried, but in the end the theory is so complicated that you have to question whether I should do something like that or just invent a particle to be the dark matter. Yeah.
Yeah, hi Professor.
Yeah.
So my question is, how can we effectively adapt and apply the way we handle Poisson short noise in another field, like for example, biochemical signal processing or other fields like that. So, I mean, the way we handle Poisson short noise in
short
field.
noise.
Yeah.
Short noise in what? In
your field. So
in neutrinos.
There are many, correct. There are many approaches how we handle short noise, right?
Yeah.
So I mean, I feel that it could also apply to multiple other fields like biochemical signal processing. So I mean, is there something different or suitable techniques that can also be applied in biochemical signal processing that you can think of?
You mean, so okay, let me see if I understand you correctly. You're asking about those simulations with neutrinos where there's short noise and how we get around it and whether they can be applied in other fields. I'm not sure I can answer application in other fields. I have no experience, but short noise in simulations, I mean, mostly you go to larger and larger computer with more and more particles, then you can beat down the short noise. But in the particular case of simulating neutrinos, there are actually ways to get around it. There are actually different ways of doing simulations that would allow you to get around the short noise problem. So one way to get around that is very simply is to not use particles. Okay, instead of using n-body particles, you can actually just solve a set of fluid equations on the grid, and that allows you to essentially eliminate the whole short noise issue with having to track too many particles that are moving too fast. Or if you like using particles, you can also use them in a smart way. So for example, there's one group of people who've been simulating neutrinos. Instead of simulating the actual neutrinos, they were simulating the fluctuations. They were using the particles to represent the fluctuations. And somehow they managed to beat down the short noise as well. So there are ways around it, other than just going to a bigger and bigger computer. But I don't know how it would apply to other fields. I don't know what other people do in other fields, unfortunately. So, yeah.
Yeah, we've had a lot of questions from the audience here, but there are also some people online who would like to ask questions, and Devdatta will ask them.
Yeah. So Priyanka Adhikari is asking, is there any possibility of creating particles when interaction of dark matter and dark energy happens?
Possible, yeah. Yeah, I mean, if you ask me on top of my head if I've seen a paper on that, I'm not sure I have, but I don't see why you cannot. Yeah.
Okay. Rahul Shah is asking, does string theory have any explanation for dark matter?
Possible again, although I think the string theorists tend to deal with higher energies, and dark matter is a bit of a low energy phenomenon. I'm not sure if I've seen too many string models of dark matter, but again, nothing to stop string theory from having something to say about a dark matter problem. It's just that it's not something the string theorists tend to deal with, from my experience.
Right. Captain Rituraj Singh is asking, what is the mass range for the axions that are produced during the QCD phase transitions? Because there are many studies that propose axion-like particles, which could be massive, around 100 GeV.
Well, okay, axion-like the QCD axion that is usually used as a dark matter candidate has a mass in the micro electron volt range. Micro electron volt may be a little heavier, maybe a little bit lighter, but not 100 GeV definitely. If you have a 100 GeV axion-like particle, it's not a wave like dark matter anymore. Yeah, that would be a different thing.
Right. Nuno Morocco is asking, is there any evidence for right-handed neutrinos?
No, not at all. People look for them. Right-handed neutrinos are very useful for all sorts of things, but no one's seen one. Just like no one's seen an axion, by the way.
Okay. Vivekanand Mahapatra is asking, how can the mass of neutrinos affect the epoch of recombination, as sterile neutrinos and relic neutrinos can provide abundant neutrinos and thus affect the epoch of recombination and CMB as well?
Sure, I mean, yes, they do. Simply because they're there and they have an energy density, they drive expansion, and so as I was mentioned before, the neutrinos are quite important as a way as energy to drive expansion at the early universe. In the late universe, they're not so important. During recombination, they also play a role. Not a very major role, but they are there.
Okay. Sahil Rawat is asking, how would neutrino dark matter interactions in the early universe change the history of the universe?
Neutrino dark matter interaction. How early do you want it? So if you have, let's say, if it's very early, probably not much, other than maybe changing the abundance of the dark matter. If you have dark matter neutrino interaction during recombination times, so CMB times, that's observable. That has an observable effect. So so it does change how we see the CMB sky, and so it's something that can be constrained.
Okay.
So it has an effect, definitely.
Okay. I think you've already answered Avni's question, who is asking why can't we detect neutrinos? We can, right?
Yes, we can, definitely. We have been for decades.
Right.
But not these neutrinos, by the way, to be absolutely certain. We have detected neutrinos from the sun, from the atmosphere, from detectors, from accelerator beams, but not these neutrinos from the Big Bang. These ones are very, very low energy, and usually particle physics experiments depend on a particle coming in, depositing some energy in your detector. And if your particle doesn't have much energy, there's nothing to deposit. So, so that's a difficulty in detecting these neutrinos.
Thank you.
Yeah.
Is
Okay.
there more questions?
I think we've had enough questions.
Yeah. There's one over there, maybe.
Okay, one last one.
One last one.
I didn't understand properly that how can we relate the mass of the neutrino with the distribution of the galaxies?
Okay, yeah. So it's simply because you make these neutrinos in the early universe. You make them just like you make photons and dark matter and whatever. But the thing is that these neutrinos, when they were made, they were very fast. They move around like crazy. And when we form structures like galaxies, what's happening is that you're waiting for these, you're looking for these things to clump together. Okay, you have gravitational clumping of dark matter, of atoms, etc. And so you form a galaxy once you clump. But if you have a lot of neutrinos around, they are pushing things out because they're fast. And so that tends to affect the, how many really small structures you can form. So for example, if you have too many neutrinos, you may not be able to form a dwarf galaxy very efficiently because they don't like to clump. Yeah? Yeah. It's just that they're too energetic. Anything that's too energetic that you cannot dissipate the energy, you cannot clump into a small lump of thing.
Okay, so we've had a wonderful talk followed by a lot of lively interaction. Let's thank Yvonne for this
Well, thank you
talk.
very much.
and present her with a memento of this occasion.
Oh, thank you so much. Thank you. Yeah, well.
So, thank you everyone. Please, time for coffee.